Hello, kiddos. So I'm noticing that a lot of y'all kind of stalled out when it came to collecting the data and putting that data in your data table and graphing it and making your predictions. So I wanted to help walk you through. Figure it's only fair since I'm not there. So let's do this so that you can have this complete data collection so you feel confident going into your quiz this week. All right, so as an individual, based on my last name is Bay, so I'm going to go with video A. And as I'm going through and collecting this data, I'm going to play it and I'm going to kind of hold it and scroll it to where I need it. You'll notice that the time will show up as 0. And right here, they're in half-meter increments. So my first distance is going to be 0 meters and 0 seconds right here. Come back, friend. I'm gonna pause it and just kind of scroll back. I don't really need the 0 meter, 0 second data point because we kind of know that if I am at position 0, my time is 0. So let's go on to the next one and collect that as a data point. So we're going to get 0.5 and 0.31 seconds. So 0.31. It's very particular here that we do not put in meters or seconds with our numbers. This part only wants numerical values. So we're going to go on and collect that next data point, which is 1 meter. And 1 meter is about 0.63 seconds. That's going to be 1. I'm going to go ahead and mark down it's 1.5 to 2.5. And then I just need to collect the times for 1.5, 2, and 2.5. I like that. So 0.93. 0.93. Next. Okay, 1.24. And for that next one, 2.5. Right about there, 1.56 is a good one. So yes, it is fun to do this in real time, but also it's pretty okay to do it with the videos as well. There's no knocking you one way or the other. So we're going to go to the next slide. And lo and behold, there are your data points from the previous graph. I'm just going to scoot it over a little bit and move my mathematical model equation thing up. Scooch that down. And now comes that A slider bar. Looking for one of those best fit lines to go through the majority of those data points. And it is about right there is pretty good. So because the green line, the blue line, and the purple line do not go through, I'm going to go ahead and hit those little color tabs to make them go away. It doesn't get rid of the entire equation, it just makes it go away. And now I have that my A value is equal to 1.6, and that can plug into this equation here. So D, my distance, is equal to 1.6 times my time. So I'm going to go down to where it has this part, and I'm going to fill that in right here. So D equals 1.6. I usually do a little parenthesis around it just to keep them separate. I guess that's my AP Physics coming in to yell at me. All right. So now you have your mathematical model. And remember, if you had the lower graph, or sorry, the lower video, then it's starting from a higher position. So you might have a different, you will have a different A value. And that was the whole point of you having the data discussion, is to figure out why some of you have larger A values than others. So hopefully with us talking about it with this video, you'll get it. All right, so we have this. Let's go over to slide 7 and do this data discussion. If you had the chance to work on this with another group or with another person who had different data, I know that this was a difficult task. I understand that. But the whole point of it was to understand what similarities there were within your graph and another person's graph. So I do want to open these. And of course, it's going to take a minute, and that's okay. Right here. So we would have seen that one group would have had a, I'm trying to say it without saying it, would have had a lower slope, and the other group would have had a higher slope. Both have the same shape. So if we're looking at similarities and differences, then we can say, well, they've both got the same equation, meaning that they've both got the same pattern, which is that proportional pattern. Hopefully you have that pattern written down in your notes. So same shape, they've got the same equation, we've got the same axis, so we're still looking at distance and time, we are still scaled the same. What are some, so those are some similarities. And why would we expect that? Well, we are still running the same experiment of a ball rolling down a ramp. The only difference we had between that first video and that second video was the height of the video. It still had the same ramp, same bowling ball, same kind of situation. So what are some differences? Well, these data points are different. So yeah, we're still looking at it in terms of, let's look here, these two data points are at maybe about 0.5, that'd be 0.6, 0.7. So 0.8, 9, be 7.5, maybe 0.8 seconds. And the red graph or the red line only goes a distance of 1.5 meters in 0.7 or 0.8 seconds, while the green line goes a distance of 2 meters in that same time. So we could say that this green line is covering, or the ball that represents that green line is covering a greater distance in the same amount of time, right? If they both occur at 0.8 seconds, but the red line goes 1.5, where the green line goes 2, then the green is covering a greater distance in that same amount of time. All right. Let's continue and kind of look at this one together. So the fastest is going to be the one that covers the greatest distance in the same amount of time. So I am looking at, for the fastest, I want the one with the greatest slope. And I do believe that that one is it. If I compare all three of them, making sure that they are all the same scale. If it's all the same scale, then you can compare it based on the line. But if it's not, then that's a problem. And the same scale means it goes from 0 to 3. This one also goes from 0 to 3 and 0 to 3. And on time, the furthest time that we have is 2 seconds, and that's the same for all of them. So we can compare now with our slope of our line. All right, and at 1 second, the way that I know how much distance it covers, if you look at 1 second, that's going to tell you. So I know this is really, really tiny, but at 1 second, it goes about almost about 2.5 meters. So that's going to be 2.5 or about 2.3 times the time. So 1 times 2.3 is going to give us a distance of about 2.3. Follow along with me. In this one, we have 1 times, it's more than 1.5, so we're following where the line is, not where the dot is. Follow the line. So when the time is 1, the line crosses it between 1.5 and 2, so about 1.7. So 1 times 1.7 would give us a distance of about 1.7. All right, and then for this last one, do that process again. I shouldn't have dragged that up there, like I know that that goes there. So we'll have that at time 1 second, that blue best fit line is going to cross at about 0.5 meters. So 1 times 0.5 is going to give us a distance of 5. So using that time of 1 second makes this analysis very, very easy. Just a tip. All right, so these questions should look, pardon me, they should look familiar because they're the same questions that are here on this dreaded slide 7 that hardly anyone did. So let's look through it. We are going to communicate the mathematical model for our system. Y'all, that is this right here. So D equals whatever your number is times T. That's our number 1. D equals, in this case, it's 1.6 times T. 2, a description of what the A constant value represents in the real world. Well, I didn't mean to go to this one. I wanted to go here. When we are looking at this, the A value represents how far that object is able to go in a certain period of time. So in 1 second, I'm able to travel 1.6, 1.7 meters. Oops, come back. So the A value represents the distance the bowling ball is going to travel and able to travel. A given period of time. All right. Hopefully your things are kind of coming together a little bit, so you're starting to get it. All right, number 3, explain why the pattern in the data makes sense. So the pattern in the data makes sense because as time continues to increase, that object is going to continue to travel the same distance for each period of time. So it's not going to be increasing its distance. It holds a pretty consistent pattern. So if we go back to our our data table, it might be easier to see it there. That we are increasing by about 0.3 seconds for every half meter. So from here, we go from 0.3 to about 0.6. That's 0.3 seconds for half of a meter. And then for that next half meter, it goes from 0.6 to 0.9. And that next half meter, it goes from 0.9 to 0.2. And then from 0.2 to about 0.5. So it's increasing at a rate of 0.5 meters every 0.3 seconds. Again, if you took data on the bottom graph, yours is going to be different. So explain why the pattern in the data makes sense. Pattern makes sense because once the object is off the ramp, there's nothing else giving it additional speed. So the ramp was there purely to accelerate the object, but once it was on the ground, there is nothing accelerating it. So it's only going to travel with the same speed it had before. So the pattern in the data makes sense because the object traveling with the speed it, trying to figure out the best word, achieved, attained, got. I'm going to go with got from the ramp. The speed is going to remain constant. I don't want you thinking this means constant, like it's not changing, as in the first pattern. So the speed is going to remain constant, meaning that the distance traveled will increase by the same amount for each segment of time. Hopefully you kind of latched on to my thought there. So for 0.3 seconds, it goes 0.5 meters, but it's consistent. We talked a little bit about how the pattern will eventually break down, and it will. That object will not travel along that floor at that same rate all the time. And the rate in this case is, we'll get to that in the next question. So restate the mathematical model in all words. So we're going to take this. Please don't just write distance equals 1.6 times time. We want to express this. So the distance, the object, the bowling ball, the distance the bowling ball travels is equal to 1.6 meters each second. I'm going to go and show you why. Remember that little trick from these slides. If you compare it at 1 second and you look at where that best line fits or best fit line hits, then you can see it. So 1.6 meters right here. At 1 second, that object has traveled about 1.6 to maybe 1.7 meters. So I'm not lying here when I say that. The distance the bowling ball travels is equal to 1.6 meters each second. Hopefully this is clicking in your head and you're going, oh, I remember certain things are measured in meters per second and that is velocity or speed. So that means that our A value represents the speed, velocity of the ball. So yes, when we're collecting that A value and the different ramp heights are giving a different speed to that ball as it's rolling down. All right, so hopefully this is coming together. And this slide is going to be our prediction. Oh, and then that little card sort we already did. Oops. So the prediction, predict how far this bowling ball is going to travel in 6 seconds. Well, you need to go back and check. We only have data up to about 1.7 seconds, maybe 1.8 seconds, and it wants us to predict all the way out to 6. All the way out here. I can't even get it on the graph. Hold on. There you go. So how confident are you going to be in your prediction? Yeah, it looks good right now, but again, that model is not going to last forever. It will break down, friction, air resistance will get in the way. So we come back over and we're going to answer. Circle your level of confidence. Well, whoops. I would say that we've got our 2 considerations. So out of these 2, do our best fit lines, are they pretty much, or sorry, are data points on the best fit line, or are the data points around the best fit line, or are the data points nowhere near the best fit line? I think they're pretty much on it. You can check yours, but I would definitely say, yeah, we're in this range, which means that we are right here. And then remember, we're going to find what this one is, and then we're going to do that battleship kind of coordination system for which one of these best works. So now, is the predicted value of, again, 6 seconds within our data range? Oopsie. Remember, our data range is from 3 seconds up to about maybe 1.7 seconds. So I don't think that we're in it. All right, I definitely wouldn't say that. I wouldn't even say that we're near it. I would say that we are way outside of it, right? 6 seconds is like way up here on this. So that means that it's going to be both of these statements that explain why our prediction is going to be medium confidence. So when you type this out, I think I might type it on the previous slide just so you can see it written out. Predict how far the bowling ball will go in 6 seconds. So I'm going to say, I predict, whoops, not typing, that a bowling ball will take, and then we can go here, or we'll travel in 6 seconds. We can use the best fit line to predict it. It's not going to be a good prediction, but we can do it. So we could say, I think it's going to be, so we go up from 6 and it is, that's 5, 6, 7, nope, 5, 7.5. The way that they do these are so weird. A little less than 10, maybe 9. So maybe 9 meters. Again, not too confident, are we? Travel 9 meters in 6 seconds. Confidence. My prediction is medium. I need to go and check that again. Yep, is medium because, and then both of these statements go in there. The predicted value is way far away. Looking at the wording, predicted value is far from the data range. And we're going to bring in that other one. The best fit line is near the center. Best fit line is near the center of all of the data points. I believe that's how we finish that. Hold on. Yep. Okay. So now you have your data discussion. Sorry again that I wasn't there to be able to walk you through this in more detail. I wanted to give you the opportunity to work with your peers and identify different graph shapes, because that's important for you to be able to do, because you need that skill for all of the other data discussions coming up. But again, we've got our data discussion down and you've got your prediction. So hopefully you can use this information and feel a little bit more confident in your quiz that is coming up. Let's see if I can give you any other tips and tricks. I think the only other thing that you really need to know, and it came up on the pre-quiz, is that when you use this A slider bar, I'm going to turn on these other graphs for these other best fit lines. So when you are using this A slider bar, your job is to find the line that goes through most all of those data points. That's your job. Doesn't matter what color it is, but your job is to find the line that goes through a majority of those points. So when you do, note that it is the red line and that each of these color lines is associated with its own equation. We are going to get to this equation, this green one. This is going to be the last one that we do. We're going to get to this blue one. This is going to be the next one, the next experiment that we do. We've already done this purple one. That was the constant horizontal for the pendulum lab. So that's how we got that the time was equal to just what it was. So we can make these go away, but the big point is the line that fits your data points is associated with an equation. So when you get into Desmos and it's asking you, what is your mathematical model? I know some of my students kind of freaked out a little bit on that for the pre-quiz. It is given to you once you find your best fit line. And I think for the pre-quiz, it was something like 15 plus A times D or something like that. But there was an equation that fit that data. So use that to answer your questions. All right, if y'all have any questions, please feel free to reach out to me, not while you're taking your quiz, but in general, if you have questions. All right, take care, y'all.